So today I'm going to talk about some SQL tricks and concepts that you might have heard about or might have not. But let me introduce myself first. So as David said, I'm the lead maintainer of Blitz.js. It's a framework, a full-stack JavaScript framework, which is now pivoting to a framework-agnostic toolkit, so that you will be able to use it like with Next.js or Remix or Svelte, possibly. I'm based in Poland, and you can find me on Twitter as Aleksandra Sikora. So my talk is split into 4 parts, and we're going to be talking about different SQL stuff in each of them. So firstly, like before we start with the main content, like why am I even here? Why am I talking about SQL? And why do I think that it's so cool? So firstly is declarative. Like you tell the machine what you want. You don't tell it how to do this. It's like, here are some constraints, go ahead, solve them. And it goes with some trade-offs, like being declarative, but what it also means is that it's only 4th generation language that got mainstream. 4th generation means like declarative and non-procedural. And everybody uses SQL. Like Prolog was kind of close to become mainstream, but it never made it. But SQL did. And it kind of goes with the name. Okay, someone is laughing, that's good. Okay, so since you're at this conference, I assume that you are more or less familiar with basic SQL. So this is like a simple query that you might have seen before. Here goes a bit more complex one, like we have some joins, there's more going on. But what about this one? Let me go to my terminal, and there's a query on the left side of your screen, which is way more interesting. Now I'm going to actually run it, and let's see what happens. So with this query, I can make it slightly bigger. So with this query, we just generated a Mandelbrot set. It's a set of complex numbers, and when you plot them, you can have this nice fractal. So this is more what we're going to talk about today, those kind of things. Going back to my slides, we're going to start with recursive common table expressions, aka the true gem of SQL. And I'm going to explain why later. So before we start talking about recursion, let's talk about the simple common table expressions without recursion. So here you can see how it looks like. We have the with keyword, and we declare the name of the common table expression. I have red cars. And then inside of it, I have a query that you can think of. It's like a named query that will produce like a virtual table. You can use this to extract some parts of your SQL queries outside of the main query to simplify your code, to improve readability. You can reuse them. Like normally, like if you would want to use some SQL, some select statement in multiple places with CTE, you don't have to do this. You can like extract it and then reuse. It also allows you to do multi-level aggregations that wouldn't be possible otherwise. So in the CTE, I can have like 1-level aggregation. I have this min, max on the grade column. And then I can have like another level of aggregations in the main query. Now, the recursion part. So here's a recursive common table expression. This specific example generates a series of 10s. So what happens here is that we have a base row set of a recursion. We're starting with 10. And then in the recursive part, we are adding 10 to the previous value. And we are doing this till we reach 100. OK, so why did I call recursive common table expressions a true gem of SQL? It's because it made SQL Turing complete. Recursion, like they added recursion, which means looping. And looping without max iteration count and unbound storage means Turing completeness. And recursive common table expressions did not only provide looping, they also let you store intermediate data and retrieve it. So you saw one example of a recursive common table expression. Now you're going to see a slightly different one. But before we see the code, I want to introduce one more thing. So you might have heard about brainfuck. I hope that I'm not breaking a code of conduct here. It's actually a name of a language. It's very simple. It has only like 8 commands, and it was made to like challenge programmers. It's not being used in production. On the right side, the thing that you see, it prints hello world in brainfuck. So someone was up for a challenge to write an interpreter for brainfuck in SQL. And that's what we're going to see. This is the code on the left side. It's only 55 lines. And now I'm going to run it in the second terminal. And we printed hello world. And we did all of that with recursive common table expressions. So we don't, on daily basis, we don't write interpreters. So we probably don't care about it specifically. But there are plenty of other use cases for recursive common table expressions. Like when you have a hierarchical data in your database, like company structure, tasks with subtasks, maybe like multi-level comments, or something similar, then they make it easy to build and get data from those like tree-like structures. And they can also traverse the data easier. And they also let you to generate like arbitrary row sets, as we saw in the first example when we generated like a series of tens. Now I'm gonna briefly explain how it works. So there's this tree. Let's say that this is like a family tree, and we are looking for all the ancestors of Jordan. So we have this base row set where we are finding a parent of a Jordan, and then in the recursive part we are using union all, and we have the recursive part that involves the recursive common table expression ancestors, and is trying to find a parent of whatever we have already in ancestors. So this may kind of look complicated that we called the recursive query ancestors, but we are also referencing it inside of it. So let's take a look at this visual explanation. So we have this base query of the RCTE, and it produces the first row set, like let's call it a base row set R0. And then this row set is being like passed to the recursive query, this recursive part that we saw previously. And it produces another row set, R1, which is then applied to the next recursive query. And we're going on and on until we reach an empty row set. So then we take all of the row sets, and they are being merged together into the final result. So going back to the example, like how that works exactly. So from the base query, we are getting the parent of Jordan is Taylor. And then we are looking for parents of Taylor. And we get Austin and Sam. And then, again, we apply Austin and Sam, and we are trying to find their parents. We're finding Ezra and Alex. Then we don't have any more information. So the next row set is empty, and we get the final result with all the previous row sets that have been produced. So that was about recursive common table expressions. And since we are already talking about tree-like structures, I'm going to show you one more thing, like how to traverse this kind of data with ease. So right now we have a slightly different tree. Like let's say this is a company structure. And we would like to find out what's the path between John and Alex. And in general, we want to be able to answer questions like, what are the relationships between nodes? We can do that with the Ltree extension. This is included in standard Postgres package, so you should be able to load it in most servers. You can do this with this create extension Ltree command, and then you can use the Ltree type for your column type. In my example, this is the column is called path, and it can be like any other name, but basically the path is like dot separated string that then you can use Ltree operators to fetch some data. So now let's see an example. I'm gonna open Table Plus. So I already created the table and I filled it with some data. Like I filled the same data that you saw on the example. And I have two sample queries. The first one is supposed to count like how many nodes there are below Alex. So if you run this, it's gonna print 9 because there are like 9 people below Alex. This operator here is from the Ltree package. And the other query I have here is this. We are looking for all the rows that have Ezra somewhere inside of its path. So you can do those kind of things, like you can use the operators to count nodes, to find the descendants and ancestors easily, but it kind of looks like some fancy string operations. So the question is, like, can't we have the same thing with Postgres string functions? And the answer is yes, but also no. So the coolest thing about Ltree is not the operators, but it's the indexing. So let's say we have this query. We're looking for a specific path in our table. If you have millions of rows, this is going to be very slow, like because Postgres will have to go through each row and do the comparison and to see if the path is equal to the string that you have in your query. Now you can add an index like B-tree index that you are probably adding to your other tables. And that's going to be slightly better. Postgres will do a binary search on your data, so that will be an improvement. But still, Postgres doesn't know what this add operator means. So eventually, it will fall back to a sequential scan. That's where generalized search tree comes into play. So Postgres lets us to define our own indexing code, and this is what the Ltree package does. It provides its own like custom function that Postgres can use instead of the default one, and this is what makes the Ltree searches fast. In that way, Postgres knows how to compare the paths, what it means that you are looking for something that's lower or greater than a particular path. So I'm going to leave a few links to read more about it in a takeaway section. And that's the gist thing. It's kind of an interesting topic to research. OK, now we're going to do some data analysis with SQL. Firstly, I'm going to state the examples that we're going to like focus on in this part. So let's say you keep track of some kind of events, and you'd like to know how long ago the previous one happened. Like, for example, you keep track of all the logins to the application. And one more thing that you'd like to know is, like, for each row, you want to know how much time passed since the very first event. For example, the account creation. To solve those kind of problems, we're going to use window functions. So here's an example of a simple window function. Here's a row number which assigns a sequential integer to each row. And what happens here is that we are we are specifying how it should behave inside of the over part. And we have the partition by age. It splits the data into blocks by age. It's kind of like a group by. And then we also have order by name, but it orders within the particular partition, not the whole data. So for the first block, we have one row with age 18. Then in the second one, we have a few more rows with age 19, and so on. Now, since I mentioned that partition behaves similar to group by, then what's like the difference? Why would you use one or the other? So with group by aggregations, you're going to have one row per each aggregation. While with window functions, you can have still one result row per one input row, which means that you can work with both aggregated and non-aggregated data at the same time. Now going back to the questions that I started with, I have a table events with just the name and a timestamp. I filled it with some data, and now here's the query that solves the examples. I'm querying the timestamp, like when the event happened, and then I'm using window function lag, which is comparing the current row with the previous row. Like the second argument is 1 because I want like one row before. I'm calling it delta, and then I also used another window function called first value, which will give me the thing that I wanted, the second example, like how much time passed since the very first event. So if I run it, I hope you can see it. Then I have like all the information I wanted, the delta and the total time that passed. Okay, so let's go to the last part of my presentation. We're gonna talk about some spreadsheets and SQL. So, as before, I'm gonna define an example that I'm gonna work with. So let's say that we have like a table with bank operations, and we would like to know a balance after each operation. But we also have this condition that it can never go below 0. So basically, for each row, we want a maximum of 0 and running total. Running total is the cumulative sum of the value and all the previous values in the column. So this is what we call balance here. So how do we do this? Can we use recursive common table expressions that we were already talking about? I don't think so. I haven't tried that, but I think it's not possible. Can we use window functions that we already saw? That's probably possible, and we could do this. But why would we do this if we can instead use some obscure, overcomplicated, and vendor-specific SQL? That's what we're going to do here. So you might have noticed that all of those questions would be fairly easy with Excel. Like, you know, you would have a formula in one cell, then you would drag it and apply it to all the other cells. Like, that would be a few minutes of work. So what if I told you that we can have Excel in the database? Specifically, we can have it with Oracle model clause. So this is only in Oracle, but it's kind of interesting, and I wanted to mention that in this talk. So how it looks like. You have the query, and then below you declare the model part. When you specify 3 things, like the dimensions by, so you're going to specify like the spreadsheet dimensions, and in Excel you only have 2, but with model clause you can have multiple dimensions. Then there's measures part. this is like the spreadsheet cell type. We're gonna specify what we want to use in the spreadsheet. And then we have rules, which is the formulas. But in Excel, you can only have one formula per cell. Here you can have like a tuple with multiple of them. So let's see an example. For that, I'm gonna use Oracle Playground. I'm gonna make it slightly bigger. So I already filled it with some data. I have this account balance table with the date and an amount. And here's the query. Let's take a look at the model statement. So in the dimensions by, I'm using window function row number to assign an integer to each row. I'm doing that so that there are no gaps between the rows, and this will be my my one dimension of the spreadsheet. And then in measures, I have like things that I care about. It's the date, it's the amount, and the total, the balance that we are calculating. And here's the most interesting part, the rule. So what I'm saying here is that for any cell in my spreadsheet, I want the greatest of 0 and the value, the previous value of total plus the current value from the amount column. The CV stands for current value, and it's built in, so we can take advantage of that. So I already ran it. Oh, I didn't. Can I run it? No, my session has expired. I'm not gonna do this right now, but you can trust me that it works. Yeah, trust me. I'm gonna leave a link so you can try it yourself later. So let's go back to my slides. That was the last thing that I wanted to talk about. So let's do a recap of what we were talking about today. So we were talking about common table expressions and recursive common table expressions. We saw an Ltree Postgres extension. We did some data analysis with window functions. And we saw how to simulate Excel spreadsheets with Oracle Model Close. If you want to learn more about those things, I included some links on my website. So if you scan this QR code, it will take you to my blog, to the speaking page, and you can find the slides there, and you can also find some links that I found interesting. Thank you a lot. Thank you for having me here. Do you have any questions?